apparently the dust-free chalk does not really work well on this chalkboard, but this very dusty chalk, I'm already covered in white, is nice and smooth. Okay, so after the discussion of practical refrigerators, where we go through a cycle with a working fluid, say for example Freon is what's commonly used, or now because the little leaking off bits of Freon gas can break down ozone, they're switching over to different kinds of I was going to say gas or fluid. Well, it depends on what the pressure is, whether it's gas or fluid. Materials, substances. And unfortunately, those tend to be not as good for refrigeration because they're pretty corrosive. So there's, in practice, there are, but they accomplish the same thing. They go through this kind of a cycle, which is really like the heat engines of the engine cycle run in reverse. So a heat engine is always run clockwise around a PV diagram, and so you get a positive amount of work done. If you integrate over the closed cycle, you will get a, well, you want to get a positive number. But when you go through a refrigerator, you've got to go in the opposite direction, which gets you a negative amount of work done. When I say work, sorry, I should mean in the sense that we have been using in the in describing engines. We define work as positive, positive output for a heat engine, and so that means that in practice it's the integral of positive PdV for a heat engine, rather than the integral of negative PdV, as we've done for the work done on a system. For an engine, it's the work done by the system that's interesting. And so you wind up getting a positive number when you integrate going clockwise around the cycle. For a refrigerator, you have, in principle, for this ideal like a Carnot refrigerator or a Stirling refrigerator, you'd simply be going around the same kind of a loop counterclockwise, and you can get the work out that way. But for a refrigerator, of course, we're interested in the work done on the system, what it costs you when you plug in the compressor motor into the electrical socket in the wall. And so we're again defining W to be positive, even though we're running in the opposite direction. Well, there's a, the book has some nice descriptions of super cold refrigeration, how to liquefy gases, and so on, and these are really just applications, and it's more verbal than anything else. I'll let you read over that on your own, but there's one in particular I want to describe, which is conceptually very different from all of the others, and that's laser cooling. Pardon me. Okay, so in this case, we want to look at what temperature really means down at the individual particle level. So remember, the temperature is a measure of the kinetic energy, average kinetic energy per particle of your gas. So since kinetic energy, let's see here. You've got a particle of mass m, it's moving with a velocity v. Its kinetic energy is 1/2 mv squared. And the temperature is proportional to the average of kinetic energy divided by the number of particles. Okay, so if you have a way of slowing down the atoms or molecules in the gas, then you can cool it. You will lower the temperature. So one way of doing this is really clever, and that is, let's say that we take an atom here, and well, let's say it's moving off to the right, like this. So how can you slow down an atom? Well, one thing you can do is, if you imagine these to be like classical billiard balls, you could simply bounce something smaller off of it. So if you've got a pool ball, a billiard ball, rolling off to the right here, if you took some ping pong balls from the left and had them moving off this direction, from the right, moving to the left, and you hit it with a bunch of those, each one will slow it down just a little bit there. And then gradually it will come to a stop or close to it. Well, in our case, what if we hit it with photons of light? Now, photons, again, are particles of light, and they carry momentum. They have no mass, but they do have momentum. So if you have here a photon of light, like that, now, the photon will generally have a lot less momentum than the atom will, but it will, in a collision like this then, the photon will, it could bounce off of the atom, it could go straight through it, or it could be absorbed. And what we will do is, we want it to be absorbed by the atom. This is called an inelastic collision. If you've got pool balls bouncing off of each other, they are pretty close to elastic collisions, which means that not only is momentum conserved, which it always is, but also the kinetic energies of the total kinetic energy of both particles is conserved. Now, kinetic energy is 1/2 mv squared. Momentum, which is a lowercase p, is simply mv. Okay. Now, so the atom has momentum mv. The photon has, well, it's got no mass at all. And it's moving at the speed of light. But it does have momentum. The thing is that for something moving at, or for that matter, near the speed of light, the equation for momentum is a little different. Like right now, I'm kind of blanking from my mind. Let me see here. I think P is E over C. Yeah, that sounds right. Where E is the photon's total energy. Divided by the speed of light, you get the momentum there. E equals P. Yeah, that sounds right. Okay. Yes, I've got that correct. Okay. If the photon is absorbed, you got an inelastic collision. Well, no matter what, momentum is conserved. Total momentum before the collision, momentum of that plus momentum of that, equals the total momentum after the collision. That's what the prime symbol means there, afterwards. Okay. If it is totally inelastic, you don't conserve the kinetic energy, you just conserve the momentum. And this will slow the atom down by quite a bit. Well, by a little bit. So you're going to hit it with a lot of photons then. So, if you've got a laser, say, so it's shooting out a stream of photons at the atom, you have a laser which is tuned so that its wavelength is just right at one of the chemical absorption lines, spectral absorption lines for this atom's chemical spectrum. So, remember that the spectrum of an atom, of any element, of any molecule, any substance, its chemical spectrum tells you what wavelengths of light will be absorbed by that atom. Every other wavelength of light is not absorbed. So if you have, let's see here, I can draw a spectrum. So intensity versus wavelength. And let's say you have some spectrum here. I'll draw what we call the absorption spectrum. So you may have spectral lines there, and so on like that. So at these wavelengths, at those particular wavelengths, light will be absorbed with some probability. At every other wavelength, light is not absorbed. It will just pass right on through. The atom is basically transparent. So, in order to have this inelastic collision where the photon is stuck in the atom, transfers all of its energy in, you choose a color of light, a wavelength of light, that's in one of these absorption lines. So you make a laser tuned to that wavelength. Pick one. All right, now, you shoot laser light at the atom as it comes toward it there. It'll slow down. But the atom would also want to eventually go back the other way. And for that matter, this only would work really well if the atom is already moving towards the laser. What if it's moving the other way? It's going to be sped up the other direction. Or what if it was sitting still, a nice cold atom, and it would be sped up the other way? So that's not going to work. Instead, what you do is you tune the laser to a frequency, to a wavelength, I want to say, where, you know about Doppler shifts? If the atom is moving towards you at some speed, this spectrum here will be shifted to the blue side, the shorter wavelength side. So I'll call this the blue end, short wavelength, and the long wavelength here is the red end of the spectrum. Where, at least in astronomy, when we talk about blue and red ends of the spectrum, we mean short wavelength and long wavelength ends. We're kind of forgetting the fact that there is violet out there on the far end of the visible spectrum, and for that matter, ultraviolet, X-rays, gamma rays, and so on. And for that matter, the red end, there's also the infrared and the microwaves and radio and so on like that. Blue and red means short and long wavelength. So, if the atom is moving towards you, the wavelengths of light that it will absorb, if you take the spectrum and you shift it a bit to the blue side, the faster it's moving towards you, the more the spectrum is shifted to the left here. If it's moving away from you, the spectrum is red shifted. It's shifted to the long wavelength side by a little bit. So, the neat trick is you can tune your laser so that if the atom is standing still, if it's not shifted at all, your laser is shining light, which is just a bit, let's see here, I'll put it, the laser light maybe is like this. It's a little bit to the blue side of one of the spectral lines. So normally it's not absorbed at all. And an atom at rest will just sit there, and all the laser light just goes right on through the past. But if it's moving towards you, the spectrum is shifted a little to the left there, and and for atoms moving at just a little bit of the right speed there, they absorb the laser light, and it slows them down if they're moving this way. And then when they slow down enough to where they're almost at rest, then they're not shifted anymore. Their spectrum isn't shifted, and they're not absorbing anything. So it slows them down and doesn't do anything once they've slowed down. That's all well and good, but it doesn't do anything for the atoms that are moving the other direction, in the red shifted direction away from you. So you have another laser on the other side, photons coming from this way, and it's tuned the same way. So for atoms that are moving away from this laser, the spectrum is red shifted for this atom, nothing happens. If it's moving this way though, then it's blue shifted from the point of view of this photon, of that laser, and it slows down if it's moving this way. And once it comes to close to a stop, it's not effective anymore. So you have a series of lasers, top, bottom, left, right, all different angles, say, each of which is tuned to a frequency, to a wavelength slightly to the blue side of the spectral line of the atom. And so you can track it that way. Make sure I've got all of these lasers here shown on the screen. So no matter which way the atom is moving, it'll be moving towards some laser, and that laser's light will be blue shifted for it and will be absorbed until the atom slows down enough. So, let's see. There are a few other practical things though as well. Let's see here. So even at very low speeds, the atoms would quickly hit the hot walls of the container. Because after all, you've got to put all this in a box. It's not like you're going to have it exposed out into the atmosphere, which is very hot anyway. You're going to have some kind of a box. Well, the box itself is, and you don't want, by the way, the atmosphere getting into this. That's actually the largest reason. Well, also, the box, even if you've got it cooled with liquid nitrogen and whatnot, the box is still going to be a lot warmer than the bunch of atoms in here is. And even at pretty slow speeds, eventually those things are going to drift over and hit the wall. The wall is hot compared to them. So it's going to give them a big kick of energy, and then they start transferring that back into this. So how do you keep them away from the edges of your container? So what you can do is you can have magnetic fields that the magnetic field will, now, I should say here, if you just have an atom sitting here and you put a magnet next to it, it does not do a thing. You need to have an electric field, a moving electric field creates a magnetic field, and that will interact with it. Well, without a moving electric field, the atoms are not really going to do anything. So, but what does a magnetic field do for you? You can use a magnetic field to change the spectrum, the absorption spectrum of the atom, and make it absorb light differently, and perhaps more strongly is what you want, as it gets too close to the edges here. So one of the things you can do is, there is the one example. In fact, I'm not really sure if they use this in laser cooling, but it would be one thing you could do. Zeeman effect and the Stark effect. By the way, have you covered either of these in physical chemistry? Okay. Then maybe they don't really have much role in chemistry, but these are two effects where you have, see, the Zeeman effect is with a large magnetic field. The Stark effect, I think actually you have an external electric field in this case. But they've got similar things. What happens with the Zeeman effect, I'll describe in particular, is that if you apply a strong magnetic field to the atom, then it splits the individual electron orbitals into separate layers, depending on whether the electron is spin up or spin down. And so you have the electrons, they go around the atom there, as they go around the nucleus. They have their magnetic field dipoles, magnetic dipoles. If they're aligned with the magnetic field, then they are in a lower energy state, and if they're aligned against the magnetic field, they are in a higher energy state. Just a little bit. And you can, normally, as they're going around there is no external magnetic field, and so they don't really do anything. They're all the same energy level, the same orbital, the same N number. But if you apply this external magnetic field, then they will, well, their own magnetic dipole, aligned or anti-aligned, makes a difference to the total energy. And so it will split the orbital, the energies, and that means that they absorb light of slightly different energies than one in the other direction. And so you can take a single spectral line, and when you apply a strong magnetic field, you can split it. I've seen in the case of the sun, I was thinking that you'd really have, let's see, angular momentum, and the dipole. Okay. Without getting into quantitative details, because I've forgotten them right now, I have seen a picture of spectral lines in the sun, in sunspots where you have strong magnetic fields, and you clearly see, in one case, 3 lines in the sunspot and 1 line outside the sunspot. So, you can use that trick and change what wavelength of light the atoms absorb as they get close to the boundaries here, so that they get an extra push away from that, and just corral them into the middle. Okay, so this is called the trap with the magnetic field that keeps them close in and away from the walls, and then you have the laser cooling that does the actual hard work there. Combined, the two of these things combined means that it varies their thickness. So the magnetic field varies their ability to absorb light depending on where they are. They absorb it more readily as they get close to the edge, and less so as they get near the middle, and this starts to corral them into the center. And this can get you down a cloud of cold atoms down to about 1 millikelvin. 1/1000th of a degree Kelvin above absolute zero. And they have now been able to make variations of the technique to get down to microkelvins, 1/1000th of a Kelvin, and even billionths of a Kelvin, nanokelvins, which is pretty impressive. Okay, so laser cooling then doesn't use the cycle type refrigeration that we discussed earlier in the chapter, but it can get very cold using a bit of quantum mechanics. Okay, we'll end up here. This is the end of chapter 4, and this is just a short section here because it's a nice tape.